The discovery of interstellar objects passing through our solar system has opened a profound and unsettling chapter in modern astronomy, forcing scientists and the public alike to reconsider long-held assumptions about our cosmic environment. Since the detection of 1I/Oumuamua in 2017, it has become clear that the solar system is not an isolated island drifting quietly through space, but rather a region periodically traversed by visitors from distant stellar neighborhoods. The more recent detection of 3I/Atlas has intensified this realization, not only because of its size and velocity, but also because of the unusual characteristics of its trajectory and apparent lack of conventional cometary behavior. Together, these properties raise difficult questions that cannot be dismissed simply by appealing to statistical comfort or historical precedent. At the core of the discussion lies the issue of orbital mechanics and the immense energies involved in redirecting an object traveling at tens of kilometers per second. An object approximately 20 kilometers in diameter, moving at roughly 60 to 70 km/s near perihelion, possesses an extraordinary amount of linear and angular momentum. From a purely natural perspective, such momentum makes significant trajectory changes exceedingly unlikely without a correspondingly massive external force. This is why, under conventional assumptions, astronomers tend to classify such objects as inert rocks or icy bodies, following predictable gravitational arcs dictated by the Sun and planets. However, when one entertains even the remote possibility that an object could be technological in nature, the analysis necessarily changes. Technology, by definition, introduces agency, intention, and the capacity for controlled energy expenditure, even if such capabilities far exceed anything currently within human reach. The idea that 3I/Atlas could exploit a temporary observational blind spot created by its passage near the Sun is particularly striking. As the object moves into conjunction, solar glare will obscure it from Earth-based telescopes for a limited period. In purely astronomical terms, this is an inconvenience. In a speculative engineering context, it could be interpreted as an opportunity. Any substantial maneuver performed during this interval would be difficult to detect in real time, especially if it were executed gradually or distributed across multiple components rather than as a single, dramatic burn. The question then becomes not whether such a maneuver is easy, but whether it is physically conceivable under known laws of physics. Angular momentum change is central to this discussion. Redirecting an object from a hyperbolic interstellar trajectory toward Earth requires altering the direction of its velocity vector by a measurable amount. Even a small angular deflection, when applied at high speed, corresponds to an enormous impulse. For the main body of an object 20 kilometers across, the energy requirements would be staggering, likely beyond any reasonable extrapolation of feasible propulsion. This alone argues strongly against the idea of the entire object executing a sharp course correction. However, the situation changes if one considers the possibility of subcomponents, smaller masses released from a larger carrier. In this scenario, the bulk of the object remains on its original trajectory, while smaller probes exploit the extreme velocities near perihelion to perform high-efficiency maneuvers. The Oberth effect provides a well-understood physical mechanism by which such a strategy could, in principle, operate. A propulsion burn executed at high speed deep within a gravitational potential well yields a disproportionately large change in orbital energy. A reverse Oberth maneuver, aimed at shedding heliocentric energy rather than gaining it, could allow a small probe to transition from a fast solar flyby onto a bound orbit that intersects Earth's path. Importantly, this does not require the probe to come to a near stop relative to the Sun. In fact, slowing down too much would indeed risk solar capture into a tight orbit, reducing the likelihood of an Earth encounter. Instead, the maneuver would need to be carefully tuned to reduce just enough angular momentum to reshape the trajectory without sacrificing the hyperbolic or weakly bound character needed to reach 1 astronomical unit. From an engineering standpoint, the numbers involved remain extreme, but not obviously forbidden by physics. A change in angular momentum per unit mass, on the order of the product of a few tenths of an astronomical unit, and tens of kilometers per second represents a large but finite requirement. The fuel mass needed would scale with the mass of the probe and the exhaust velocity of its propulsion system. If one allows speculative technologies, high-energy density fuels, advanced nuclear or beam propulsion, or propulsion methods not yet conceived, the constraints become looser. This does not make such a scenario likely, but it does make it non-trivial to dismiss outright on purely mechanical grounds. Beyond the technical discussion lies a deeper psychological and philosophical dimension. The discomfort many people feel when confronted with these ideas is understandable. For centuries, humanity has grown accustomed to viewing the cosmos as largely indifferent and inert, governed by blind physical laws that, while sometimes destructive, carry no intent. The possibility that interstellar visitors could be artificial challenges this worldview in a fundamental way. It introduces uncertainty not just about astrophysics, but about humanity's place in a potentially populated and technologically diverse galaxy. This is why the reflexive dismissal of anomalous data can be counterproductive. Science advances not by clinging to comfortable narratives, but by rigorously testing hypotheses against evidence, even when those hypotheses are unsettling. The absence of cometary outgassing from 3I/Atlas, if confirmed, adds another layer of ambiguity. While there are plausible natural explanations, such as an object depleted of volatiles or possessing an unusual surface composition, the coincidence of multiple anomalies inevitably attract attention. Size, velocity, trajectory, origin, and behavior together form a pattern that feels, at the very least, worthy of careful scrutiny. History shows that major scientific breakthroughs often begin as uncomfortable questions that challenge consensus thinking. It is also important to emphasize that acknowledging uncertainty does not equate to predicting catastrophe. Speculation about technological origins does not automatically imply hostile intent, nor does it mean that an encounter is imminent or inevitable. The universe may be full of probes, debris, or relics of long-extinct civilizations, drifting silently, without purpose. Even so, prudence argues for awareness rather than complacency. Preparing mentally, emotionally, or even logistically for low-probability, high-impact events is not irrational. It is a basic feature of human risk management. When considering timelines, the earliest plausible arrival of any Earth-intercepting objects derived from 3I/Atlas would likely be months after perihelion, assuming small probes and carefully optimized trajectories. Such objects would still need to contend with detection by modern surveillance systems, which are far more capable than those that first noticed Oumuamua. This means that even if something unusual were en route, it would not necessarily arrive without warning. Uncertainty cuts both ways. It limits our ability to predict threats, but it also limits the likelihood of perfectly concealed approaches. Ultimately, the broader value of this discussion lies not in fear, but in intellectual honesty. Entertaining unconventional hypotheses forces the scientific community to sharpen its tools, improve its observational coverage, and clarify the assumptions that underlie its models. Whether 3I/Atlas turns out to be an entirely natural interstellar body or something far more exotic, the process of asking hard questions is itself a sign of healthy science. Humanity's long-term survival and growth depend not on comforting stories, but on our willingness to confront reality as it is, even when that reality is strange, ambiguous, and unsettling.